Today we are going to look at solubility product. Solubility product, or what you call KSP, works for sparing soluble salts. And the definition says is the product of the concentration of ions raised to their appropriate powers or raised to powers of stoichiometric coefficient in a saturated solution of a sparing soluble salt of an ionic compound at a given temperature. When you talk about sparing soluble, it means we get any salt that is sparingly soluble. Let me say it is calcium carbonate. If it is calcium carbonate, we are going to add there water and we shake much as it will not dissolve away, but there is some percentage or some little degree of calcium carbonate that will go into solution. That's what we are looking at. Now we are saying we should look at the concentrate or the product of ions are raised to their powers of stoichiometric coefficient in a saturated solution. It means now if we consider some of the insoluble salts, silver chloride, day-2 iodide, then we have calcium hydroxide. And if you are to write the equation showing how these salts are able to dissolve in water, that is sparing dissolution, we shall have, let's write for silver chloride, shall have silver chloride solid plus water. Here we are going to represent water as HU, aqueous. Then we shall be able to ionize, to dissolve it. We form silver ions, aqueous plus chloride ions. Now what we are saying, the constant of dissociation, that is KSP in this case, it will be equaling to the product of the concentration of the ions. These are the ions, we have silver ions, then times that of the chloride ions, that is at a constant temperature, or that's why we are saying at a given temperature. Now we have a coefficient 1 here. That's why I'm not putting it there, but it is there silently. So in writing KSP, the concentration of the solid and the water will not appear in our KSP expression. Maybe this is very easy. Let's write lead-2 iodide. Lead-2 iodide, this is lead-2 iodide, solid plus water. It's going to give us, that is lead-2 ions plus the iodide ions. But now when you look at this, we are seeing 2 iodide, meaning we shall balance them with a 2. Now if you are to write the KSP expression, it will be equaling to the product of the concentration of lead ions, lead-2 ions, times that of the iodide ions. But remember, in the definition we are having that the concept of being raised to the powers of the stoichiometric coefficient. We are meaning this equation you're writing. So you can see we have a 2 here on the iodide. We are going to put a 2 there. Now for calcium hydroxide, it's going to be obvious. This is calcium hydroxide, like that. Calcium hydroxide is also sparingly soluble. So in this topic, we don't regard anything to be 100% insoluble. We shall have calcium ions plus the hydroxyl ions. But now this side they are going to be 2. Now what you are going to do, if you are to write the KSP for this, KSP is going to be the product of calcium ions times that of the hydroxide or the hydroxyl ions. But because of these 2, we shall raise the concentration of hydroxyl with a 2. Let's look at this question. The solubility product of silver carbonate at 200 Kelvin is 8 exponent negative 2 mole cubed dm negative 9. What is the solubility at this temperature? Now we are going to begin with writing the equation for silver carbonate plus aqueous, giving us giving us silver ions, but silver ions are going to be 2 plus the carbonate ions. Now if you are to write KSP, it will be equaling to the product of silver ions times that is powered by 2 times that of the carbonate. Now if you are to let the solubility of silver to be X, it means silver carbonate to be X, it means silver ions it will be 2X, then this is going to be X. This is going to give us 4X cubed, and our X will be cube root of 8 exponent negative 2, then divided by 4, and our X, which is our solubility, is going to be 0.27. It's going to be 0.27 moles per dm cubed. It is solubility. Subscribe to your Science Pal for more videos.